Hi, it's Ms. Hochstetter to show you how to do the focus on energy diagram levels. So it starts off saying, determine the energy in electron volts of a hydrogen atom that jumps from N6 to N4. Okay, so this means that if we go to page 2 in the reference table where we have these diagrams, we are looking at N4 and N6. So those numbers are here. We have to look at the table to get them, and it can be a little tricky, as you can see, because the lines get a little bit close. But that's what we're going to look at, and we want to know specifically the energy in electron volts. So if we look at our modern physics equations, we are going to be looking at the energy of the photon from the initial minus the final. So the initial, in this case, it said N6 to N4, so we're going to do, this value is going to be my E initial, and this is my E final. So I'm going to be subtracting those two numbers from each other. So let me just scroll up. So that's going to be negative 0.38 minus negative 8.85, 0.85. And these are in EV. So you'll see it's a minus, so that becomes a plus. Either way, no matter which way you do this, you're going to want to take the absolute value of this, because energy is a scalar quantity. It doesn't depend on direction. So when you do that, you're going to get 0.47 EV. Whoops. And, sorry, go away. Okay, there we go. All right, and then it says determine the energy in joules of the hydrogen's transition. So to do that, we're going to have to convert 0.47 electron volts, and we're going to want to convert it to joules. So we're going to have to do some dimensional analysis here. And so you're going to have to go to the first page of your reference table, and you're going to look for 1 electron volt is equal to 1.60 times 10 to the negative 19 joules. And what you'll see here is EV cancels out with EV, so we're going to be left with joules, which is what we want. And when we do that, we get 7.52 times 10 to the negative 20 joules. So it's not a lot of energy because it's a very tiny amount of joules, but that's why we have the different methods. So EV sometimes is easier to do energy conversions with, or sometimes joules, but you'll need to know how to convert back and forth between them. I'm going to go ahead and go on to question 5 and skip 3 and 4 since it is related to hydrogen, and we are working on the hydrogen part right now. Every now and then on the focus it'll switch to Mercury, so just be careful how you solve for this. So this is saying calculate the frequency of the electromagnetic radiation. So basically that's a fancy word for light. Calculate the frequency of the light absorbed or emitted by the hydrogen atom. So because we went from N6 to N4, that means that the electron released energy, so it emitted energy because it was coming back down towards the nucleus of the atom. But we want to solve for frequency, and we know the energy, so we're going to use this equation in the reference table, which is this one right here. And we're solving for frequency, so we're going to use this version of it. So my energy, we want to use it in joules because Planck's constant is given to us in joules. So 7.52 times 10 to the negative 20 joules equals, and you'll have to look up 6.63 times 10 to the negative 34 joules times seconds equals frequency. You're going to solve for frequency by dividing by Planck's constant on both sides. Notice joules cancel out. And when you do that, you're going to get 1.13 times 10 to the 14 hertz, which is the frequency of the white light wave. Now, this particular light wave is below the visible spectrum, so it's not going to be a color in this case. So it's going to be infrared light. In this case, it didn't ask you for what specifically it was, but that's how you would look at it. So then if we jump over to this other one, it says determine the energy in EV of a mercury atom that jumps from level G to level B. So again, we're going to have to go back down to the diagram. We're going to look under Mercury, and it said from G to B, So we're going to look at G to B, and so this is my initial, and this is my final. So negative 2.48, negative 2.48 minus negative 5.74, 5.74, and these are all in EV. So you would do that math, and you would get 3.26 electron volts, and that is the answer. Okay, and then it says determine the energy in joules of Mercury's transition. So just like we did over there, we have to convert electron volts into joules. So 1 electron volt is 1.60 times 10 to the negative 19 joules. Electron volts cancel out. You multiply that straight across and you get 5.22 times 10 to the negative 19 joules. All right, that is it.